My name is Woytowitz, and this is my video on proving a derivative does not exist at a point. To figure out how to do this, we need to know what a derivative is. A derivative is really just a limit that's equal to a slope. If we were to take the limit of the bottom of this parabola here, we'd get a y value. The derivative is just the limit, but it's equal to the value of the slope of the tangent line. So we can see coming from the left side that the derivative is approaching 0 at that point. And from the right side, it's also approaching 0. So since they are approaching the same real number, then that derivative exists. Here are 4 reasons why a derivative may not exist. The first is a removable discontinuity, such as a hole. The second is if a function approaches infinity or negative infinity. The third is a sharp corner, and the fourth is if the function is a vertical line at that point. And I'll explain why each of these derivatives does not exist. Now, the first reason a derivative may not exist is since you have a removable discontinuity at your point. A removable discontinuity would look like this, where you have a hole, whether or not that point is replaced. Now, we may think, oh, this derivative does exist, since the limit of the slope from both the left and the right side do seem to equal each other. But there is a rule that states that if a function is not continuous at that point, then it is not differentiable at that point. Now, the second reason your derivative may not exist is if your function is approaching positive or negative infinity. We can see here that this function branches out to both positive and negative infinity at the same point. Since those left and right derivatives are unequal and they're not approaching the same value, then we can concur that that derivative does not exist. Now, the third reason your function may not exist is if you hit a sharp corner. As we can see here, we have the function that looks like y equals the absolute value of x. These are 2 straight lines that hit a corner at the same point. Since the derivative from the left side is always -1 and from the right side is always 1, then they are unequal at that point at 0, 0, and therefore the derivative does not exist at that point. This is the fourth and last main reason why your derivative may not exist. If you have a vertical line at your x value, like we do here at x equals 0, then the slope of your tangent line is going to be equal to infinity, which is not a real number, and therefore that derivative does not exist. Now, here's an easy example problem of something you may see where you can apply these skills. Does the derivative exist at x equals 3? Now, the first thing you want to do to find if your derivative exists is say, hey, is this continuous? This is very obviously not continuous, so you can already tell that the derivative does not exist at that point. Another way that you can tell is since the derivative from the left side does not equal the derivative from the right side, then this derivative doesn't exist. The derivative from the left appears to be 1, and from the right appears to be 0, so therefore they aren't equal, and this derivative doesn't exist for more than one reason. Here's another problem for you to do. You can pause the video here and then hit play when you're done to hear my explanation. Okay, so the most obvious derivatives that do not exist here are going to be our removable discontinuities, which occur at -2 and 2. And our reasoning for that would be that it's just discontinuous, or that the derivative from the left and right side do not approach the same value, and the limit does not approach the same value. We can see at -4 we have a sharp corner. We can say that that derivative does not exist since the derivative from the left and right side do not equal each other. At x equals 0, our derivative, the slope, is going to be equal to infinity, and so the infinity is not a real number and therefore does not exist, and our derivative does not exist. At finally x equals 3.5, we see another sharp corner, and that derivative does not exist because the derivative from the left and right side do not equal each other. Here are the 3 most common mistakes that students make when doing problems like this. The biggest and most important one is the first one here. People say, oh, it's continuous, so that means it's differentiable. That is absolutely wrong in like every way possible. If a function is differentiable, then it has to be continuous, but not the other way around. Take an absolute value, for example. There's no holes in an absolute value function. It never goes to infinity except for at its endpoints. But yet, it is not differentiable at that one point where there's a sharp corner. Anything with a sharp corner is usually continuous, but it is not differentiable. That first one makes no sense. I do not know why people say that. The second one, people forget to look for vertical lines. That happens a lot, where you just look for your sharp corners and your removable discontinuities. You forget to look for your vertical lines. That's a really important one, because when your slope is equal to infinity, infinity is not a real number, so it technically doesn't exist there. And the third one is, even if slopes of holes equal each other, meaning the slope from the left and right side, then it is not differentiable. People say, oh, those slopes equal each other, so even though they're at different y values, then that is still differentiable. That is incorrect. Since it's discontinuous there, it's not going to be differentiable. Here's one more really hard problem for you from 2003 AP Calc AB test number 6. G of x is defined as k times the square root of x plus 1 from 0 is less than or equal to x, which is less than or equal to 3, and m times x plus 2 from 3 is less than x, which is less than or equal to 5. F of x is defined as the square root of x plus 1 when 0 is less than or equal to x, which is less than or equal to 3, and 5 minus x when 3 is less than x, which is less than or equal to 5. A. Is f continuous at x equals 3? Explain. B. If g is differentiable at x equals 3, what are k and m? C. Is f differentiable at x equals 3? Explain. Go ahead and solve this, and then come back and hit play and watch me solve it. So this is my explanation of the problem. I left the questions at the bottom just for reference. So for part A, you're going to set each part of the piecewise equal to each other, and then plug 3 in. You get 2 as each y value, and so the answer is yes, because the left and right limits are equal to each other. In part B, you set them equal to each other as well, and you plug in 3 once again. You will get 2k equals 3m plus 2. Then, you can take the derivative of each one and set it equal to each other, and you get m equals k over 4. Then you use substitution, and you can get m equals 0.4 and k equals 1.6, or 2/5 and 8/5. In part C, what you're going to do is you're going to separate the piecewise, and then take the derivative of each one. For the derivative of 5 minus x, you get negative 1. And for x plus 1 to the power of 1/2, you get 1 over 2 times the square root of x plus 1. When you plug 3 into each of these, they do not equal each other, and so therefore the answer is no, because the left and right derivatives are not equal. Thank you for watching. I hope this helped you figure out how to solve these kinds of problems. And as I stated in my last video project, Mr. Farrar, if you're watching this back from my letter of recommendation, please do assume that I was a great student and your favorite.